Hello everyone. So last video I have explained about basics in state space analysis. Okay. So this one, it is a black diagram representation of state model of a linear system. So here already we know that for the linear time invariant systems as well as linear time variant systems. So if it is a linear time variant systems, x dot of t equal to a of t into x of t plus b of t into u of t. And output equation is y of t equal to c of t into x of t plus d of t into u of t. It is for time variant systems. If it is a linear time invariant systems, these matrices A, B, C, D, these are the fixed values. Okay, if it is a linear time variant systems, this matrix is also in terms of time, that is A of t, B of t, C of t and D of t. Okay, so these expressions, that is a state model, we can say here first expression it is called state equation and second expression is called output equation. Both combinedly those two equations are called state model. This state model can be represented in the black diagram is like this. Now you see here x dot of t is equal to a of t into x of t plus b of t into u of t. This is a one expression, state equation, right? Second expression, that is output. Output expression is y of t equal to c of t into x of t plus d of t into u of t. It is a very simple black diagram only. If it is a linear time variant invariant systems, so this a of t, b of t, c of t and d of t matrices are constant values, right? So at that time, so a of t is nothing but a, b of t is equal to b, c of t equal to c, d of t equal to, that means those are not depending upon time. At that time these are the fixed values, right? Next, so if it is a general form of state and output equations, or you can say state model for a linear time invariant system, can be written as, so x dot of t you can write, or x dot equal to, it is a general form, ax plus bu, and output equation is y equal to cx plus d. Right? First one is state equation and second one is output equation. Okay, where these matrices A, B, C and D, these are the matrices. A is called system matrix, B is called input matrix and C is called output matrix and D is called transfer matrix, or it is also called direct transmission matrix. Okay, and X is a state vector, U is the input, Y is the output. Okay, next, the state space representation using physical models. Just now we have discussed about state model, right? So those state model we can represent in different ways. So one of the way is by using physical variables, second one by using phase variables, and third one by using canonical variables. Now we'll start with the first one, state variable representation or state space representation using physical variables. In this, in state space modeling of a system, the choice of state variables is arbitrary. One of the possible choice of state variables is physical variables, this one, right? So the physical variables of electrical systems are current or voltage in the R, L and C elements. Okay, already we have active elements and passive elements. Current and voltage are active and RLC, resistance, inductance and capacitive elements are passive elements. Okay, the physical variables of electrical systems are current or voltage in the R, L and C elements. So active elements current and voltage and passive elements resistance, inductance and capacitive elements. The physical variables of mechanical systems are displacement, velocity and acceleration. Okay, either if you are taking electrical systems or mechanical systems, we can find out the physical variables. Based on that, we can select the state variables. Okay. The advantage of choosing physical variables of the system as state variables are the following. First one is, these state variables can be utilized for the purpose of feedback. So these are the state variables we are selecting as a physical variables. Those are utilized for the purpose of feedback. And second one is, the implementation of design with state variable feedback becomes straightforward. Generally in the design part it is. The implementation of design with state variable feedback becomes straightforward method. And third one, the solution of states equation gives time variation of variables which have direct relevance to the physical systems. These are the advantages if you are selecting physical variables as state variables. But it has a drawback also. In choosing the physical quantities as state variables is, the solution of state equation may become a difficult task. Okay, it is a little bit difficult for finding solution of state equation while selecting physical quantities as state variables. Now, we'll take one of the example. So, how you should select the physical variables as state variables in electrical systems. Now, let us consider a state variable formulation for a simple electrical system which is RLC network shown in figure. Okay. Here, this is the network figure. Active elements, remaining all are passive elements. 2 inductors are there, 2 resistors and 1 capacitor. Here you have to find the state variables. You need to select. The state variables for this circuit are assigned by skillfully. You have to use this. Skillfully selecting the electrical parameters as state variables. Generally, physical variables are considered as state variables. That means the current through the inductor or the voltage across the capacitor. These are chosen as state variables. That is in conventional methods. In the conventional method, current through inductor and voltage across the capacitor are chosen as state variables. So here you see the circuit equations are written such that you know how to write the expressions. Already you have basic formulas like KVL, KCL. Those simple expressions only we are using here. Okay, and another thing is, here we are taking all our first order differential equations only. Right? So, just you apply here. You take here at this node particular. At this node, all the currents, you can say sum of the currents is equal to 0. You know that is a KCL only, right? Entering currents is equal to leaving currents. If you see here, all the currents are leaving at this node, right? I1, I2, I3. So, I1 plus I2 plus I3 equal to 0. What is I1 here? I1 plus I2 plus what is I3? Directly we can find out here. That is nothing but what? C into dVc by dt. Right? It is a current through this branch. Similarly, we can apply, it is a one loop, this is another loop. For this loop, you can apply KVL. For this loop also, you can apply KVL. Right? Applying KVL for loop 1, this is the first loop and this is second loop for loop 1. So what you will get here? L1 into di by dt minus this one directly, Vc plus R1 into I1 plus E of t, right, in this is equal to 0. Similarly, apply for the KVL for the second loop, you will get L2 into di by dt minus this one minus Vc plus I2 into R2 equal to 0. Okay. Then, so if we observe these three expressions, already we know current through the inductor and voltage across the capacitor. These are the state variables. Now, how many you have? Total three variables are selected as the state variables. Two from the inductors and one from capacitor. Right? So, these expressions, just you separate here dV by dt. It is the first order, right? You just keep it left side, remaining you keep in the right. Similarly, di by dt, di2 by. Okay. Now, you see here. Here the variables I1 of t, I2 of t and Vc of t chosen as state variables. X1 of t, X2 and X3. Why you are taking? Because this one it is, what is I1? It is current through the inductor 1. I2 is current through the inductor 2. And Vc is voltage across capacitor. That's why you have selected as state variables. That we are assuming this X1, X2 and X3. Okay, in this order. Now, same expressions we can represent in terms of state variables. That is just substituting X1, X2 and X3. Now you see here, left hand side, this is the first one. Which one? L1 di1 by dt. Right? We are taking as L1. What is I1? X1. X1 dot is equal to minus R1 into X1 plus X3 minus U of t. Same expression only, just substituting the value. This is the first one we are taking, this is second and this is third one. I1, I2 and this one we are taking as Vc, third state variable. Okay. Now just arranging, substituting these values in the above expressions. You will get these three expressions. Now, when you are representing in state model, so that means just you have to take here x1 dot, x2 dot and x3 dot. Shift these values to the right. What you will get? X1 dot equal to minus R1 by L1 into x1 plus, there is no x2, right? 0 plus 1 by L1 into x3 minus 1 by L1 into U of t. Right? That is the first expression. Same thing, just you see here how you are representing in vector matrix form. X1 dot, that is the first one, it is equal to. Okay. So when you are representing in state vector form, X1 dot equal to, from this expression only, minus R1 by L1 into X1 plus 0 into X2 plus 1 by L1 into X3 plus minus 1 by L1 into U. That is the first expression. Similarly, remaining two expressions also they are representing in vector form. Right? This is the state vector x dot equal to A into X. It is a state vector plus B input matrix into U. Okay? If it is error, because U of t is nothing but here error. And output, how you are taking it is across the this one. Right? So that one we are taking here. So output in terms of this y equal to R2 into X2. Right? This one only. That's why you are taking here. So y of t equal to R2 into X2. R2 into I2. I2 is nothing but what? X2. Because we have selected as state variables. Right? So that one we are representing again in vector matrix form. So in this way we can find the state model. So this is the, which one? State equation, and this one it is output equation. Combinedly, these two expressions are called state model. So that is the way to find the, to represent the state model in by using physical variables. Okay, thank you.